that the shortest time interval between the actual samples, the closer the relationship between the actual Fourier transform and the adjusted DFT was. Did you all notice that? No? Well, when you did all this, isn't that what you actually saw? Did you see that or not? Well, that was the idea, that you were supposed to be exposed to that if you did it. It shouldn't have been a very tough one. I gave you the code, basically, you know? You just have to change a few things. You couldn't run it? That should have ran. Thank you. Now, today, first I'm going to take questions about prior homework or any homeworks at all. Prior homework, like the projectors on. Anything at all?
The Wi-Fi is not doing
So, what can you? What did you say?
I think she's pulling something up, but the Wi-Fi's not great, so just take it.
Oh. Did anybody have questions about the homework from Monday at all? I didn't do this. You asked me one question. Did you have any others? I was trying to race through that. Yes?
This is Monday, and it's e to the negative 2n times sine,
Well, e to the what?
negative 2n times
Times pi?
sine,
Sine.
pi over 4 times n, times un.
And you wanted the actual DTFT for that? Well, this one is, I'm just going to say this one's pretty straightforward. If you look here, if we have first e to the minus 2n times u of n, and we want the transform of that, just take a look at that for a second. Isn't that really e to the 2, or better yet, isn't this equal to e to the minus 2 to the n power u of n? Do you agree with that, class? First, you have to agree with me. Do you all see that?
Mm-hmm.
Now, if that's the case, I'm going to make a point. A to the n u of n is a transform pairing you need to know for both dt, ft, and today's z transform. You're going to have to know this one. Most of you probably do know this one. What is it? It's 1 over what? 1 minus a times e to the minus j omega, isn't it? You agree with me? I mean, do you see this, Kenny? Now, what is a here? Isn't a really just e to the minus 2? Right? So for this one, I can say this transform pair would be simply 1 over 1 minus, and then it would be a, or e to the minus 2 here, times e to the minus j omega. This is one way of writing it. Do we agree with that? Do y'all see this right here? I know it's a dreary, yucky day, but follow me on this. It's kind of muggy in here too. Are you with me? Now, use the properties. That's a sine, right? So what do you know? If you have any x of n, and we know the relationship to x of capital omega, right? then if we have x of n times the sine of omega naught n, that goes to what? Simply j over 2 times x, right? Of omega plus omega naught minus, right, x of omega minus omega naught. Do you agree with me? Here, your x of n is this. Think of it like that, in that relationship, right? So if I'm going to have this thing multiplied by the sine omega naught here is what? By inspection. Pi over 4. So I can say that really, if I have e to the minus 2n times the sine of pi over 4n times u of n, I can come over here and say it's j over 2. Then I take the actual transform pairing right here, and now I replace omega simply with omega plus omega naught. I put it as 1 over 1 minus e to the minus 2 times e to the minus j quantity omega plus pi over 4. And then I put minus 1 over 1 minus e to the minus 2, right? And then it's going to be times e to the minus j quantity omega minus pi over 4. And that would be it. That's the correct answer. If you want to get a common denominator, you can. Anybody see something I can do with this right here? Can I what? I can add them if I wanted to, right? I could put minus 2 plus that, but this is completely legit there. All right? If you want to take 1 over e squared, you can do that, but this is the answer. Isn't there any question about that at all? By the way, if you looked at this, where are the relative signal peaks here? Just take a look. Let me go a step backwards. When I look at this one, what value of omega has the relative peak? Think about when omega is 0, what is e to the 0? Well, I have 1 over 1 minus e to the minus 2, right? Now, as omega gets larger and larger, all of a sudden it'll cause the sign here to become minus 1 when it's e to the minus j pi, isn't it? Right? E to the minus j pi is minus 1. Do you agree with me? Then you would have 1 over 1 plus e to the minus 2, right? That would be a minimum value. Do you follow me on this, class? What it tells you, you can plot this, but really is the maximum value of this, in general of this, will occur when omega is 0. That's where you have 1 over 1 minus a. Now, when you have something like this, it's not where omega equals 0, it's where omega is equal to minus pi over 4 will be the first peak, and the second peak will be at omega equals pi over 4. And if you actually plot these, you'll see 2 relative peaks at those 2 points because of the sign modulation. Does that make sense to everybody? All right. Any other questions about the prior homework? They weren't hard at all. None?
What would be like the DFT of that? Or could you do?
Yeah, you can actually take this. Now, I put that up there. And when you look at DFT, you need a finite number of samples, right? So if I say that I have this functional form right here, e to the minus 2n u of n, I have to say how long it exists. Does it exist for n equals 0 to say 20, 0 to 5? You see what I'm saying? Now once you know the number of samples, once you know that, then you can come over here and basically say that omega n here would be equal to 2 pi over cap n times nk. The n's go, so you can say omega is 2 pi over cap n, the number of samples times k, where that index would go from 0 to capital N minus 1. And then this would represent that over the range, like if you had, say, 32 samples. You're basically sampling the DTFT at that interval. And I think I put that up there in OneNote too. Do y'all see that little expression for comparing DTFT to DFT? it was a link and they did it. It's a very good actual example on that. Any other questions about the prior homework? Do y'all have tests today or something? No? Weird. I'm weird too, but go ahead.
So say if that was x of omega equals that, and then.
Whoa, 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 whoa. X of omega equals what?
Equals the top.
That?
Mhm.
Well, I have to change n to omega, don't I? Right?
So it'd be duality.
You, wait, I would take a shot at that. If I'm in the frequency domain with a DTFT, I'm always looking at, with a DTFT, I'm looking at duality continuum, all right? If I can't do duality, then I have to do the definition of the inverse, and that's an integral of, I don't want to go too far afield, but now's as good a time as any to put this up here. And then, because you'll see where we're going next. People, you don't need to copy this down right here, but for the purposes of where I'm going, this will help. I'm going to start with the actual Fourier transform. For the Fourier transform, I know x of omega is equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt. That's analysis of a signal, right? Now, if I wanted to synthesize a signal, then I would say x of t would be equal to 1 over 2 pi, the integral from minus infinity to infinity of x of omega times e to the j omega t d omega. The reason I'm using the word synthesis, filter properties. X of omega could represent filter properties that you want. You want supposedly a low-pass filter, maybe not ideal, but something reasonable. Then this would give you the impulse response to that. Instead of x of t, it would be h of t. Are you with me? But it's nevertheless, this is synthesis. You can synthesize filter operations and know what the signal would be coming out of them, if it was an impulse or any other input. This is an analyzing a signal. You're analyzing a waveform to see what the frequency content is. This is very important. This is continuous time. Now, the next thing I'm going to do below here is show you for discrete time. There, x of, our book uses capital omega, and I want to make something clear. Some books use small omega here. Some books will have x of e to the j omega, small omega, where omega is implied to be the omega associated with the DTFT. So these symbols are adjusted at times. Understand, class? Well, this is going to be equal to the sum, right? That's still a summation from n equals minus infinity to infinity of x of n times e to the what? Minus j omega n. And that is analysis of a sampled signal. There's nothing in here that says what the time interval of sampling is. You follow me? It's always implied. It's just like when you did frequency domain analysis with circuits. It was implied what omega was. Do y'all remember that? You didn't put down, a lot of times when they did it, they'd have 10 at 30 degrees as a voltage source, right? It was assuming it was 10 cosine of some frequency, omega naught t, right? But they didn't state omega naught explicitly. They would just put the impedances like minus j 5 ohms, plus j 10 ohms, plus 10, something like that. Are you understand that? Well, here, it is implied, they don't state it, but the actual sampling interval between points would be implied or stated elsewhere. Now that's analysis. Synthesis would be what? Does anybody remember this? It's almost identical to that, right? Almost identical. It's 1 over 2 pi. Keep going. Very good. The limits are now changed. They're shortened from minus pi to pi. Of x of, this would be capital omega. It would be e to the j capital omega n, or n omega, and it's d omega. So these two are nearly identical except for the limits of integration. In every other respect, they're the same. And we can use duality because of that. Now again, this is dt ft. Right? The next one we did, you might say, in the Fourier continued frequency domain, was going to be the actual DFT. And the DFT is what? Now we have x sub k, where k is an index, right? 1, 2, 3, 4. It's not a specific frequency. And we say that that is equal to what? The summation of now n goes from 0 to n minus 1, so there's a finite number of samples, n samples. And then it's going to be x of n. And then it's going to be e to the minus j 2 pi over n, right? And it's this to the n and then the k power. I break out the nk power because I like to make sure you see it's always e to the minus j 2 pi. That's 2 pi is 360 degrees divided by the number of samples. That tells you the, you might say, the angular increment of each one of these, for lack of a better term. Now over here, that's still analysis. If we wanted synthesis, if we wanted x of n, we could get it by saying that was 1 over n, right? Now it's the summation, and they like to use k here. K equals really 0 to n minus 1 of, and then you put down x of k here, then it's times e to the now plus j 2 pi over n to the nk. In other words, I've got a 1 over n scale factor that appears here. Follow me? The ones prior, your scale factor was 2 pi. Here it's 1 over n. All right? And if you want to know in MATLAB, you can do this one. You need 2 to the n samples to do it exact. And there, for MATLAB, this command right here to get that would be x of k is simply equal to fft of whatever your x is. And over here, the MATLAB command to get this would be x here would be equal to simply ifft. Of capital X, okay. And that's how you get one from the other. It works perfectly. Did anybody try this, by the way? Y'all tried this, didn't you? That works perfectly, right? Well, if you get that and want to find out what you got it from, you can put ifft of x of k and you'll get the original vector back. You can try it. Something to know. All right. So now we got Fourier transform, discrete time Fourier transform, and finally something we can use a computer to do, the DFT. There's one other thing we did. We talked about we can use the DFT and adjust it, right, with a certain value for omega. And we can go ahead and then get the actual approximate Fourier transform of that waveform, the actual Fourier transform that you would see in your tables, or you could compare it to. Do you remember that? How many remember that? This was an important thing we did. So to compare, we could say that the actual Fourier transform, x of, and now it's omega, is equal to what? Remember? It was what? 2 pi over n, right? I should say omega sub k. And what was it? Divided by ts, right? You remember this times k is equal to what, people? You did this and turned it in, didn't you?
Yeah.
What happened here? I had 1 minus e to the minus j omega, right? Times ts, I'll get what omega is, over j omega, right? And then it was times just x of k. Here, what was the omega replaced with? 2 pi over n, ts, right? Times k. This is really omega sub k. It goes here and here. And then you could do a direct comparison. And you should have saw, when you did this, this is what you just put in, that when the difference between the values x of n and x of n plus 1, the smaller that difference became, or really the spacing between those intervals became smaller, the comparison between the actual Fourier transform and the adjusted DFT were almost negligible. Did you all see that? Remember I put that up there? I even used the the actual laptop here to show it. Do y'all remember that class?
Yeah.
All right, here's where we're going next, and this is important. All this kind of leads me into my next thing. And that's going to be, I'm going to erase this, because this will fit. The next thing is going to be Laplace transform in relationship to now the Z transform. And you'll see this. For the Laplace transform, what was the big deal? Now I could say x of s, right, was equal to the integral. The limits go from 0 to infinity for on one side of Laplace's. It's x of t, and it's times e to the what? Minus st, right, times dt. Here, s is actually equal to some constant, sigma, right, plus j omega. And we note here that if, in fact, we allow s to be just j omega, we get the Laplace transform, we get the Fourier transform for anything where the signal x of t has values that are non-zero only for t greater than or equal to 0. So the Laplace becomes the Fourier transform for all functions, say, that start at 0. Time functions. Follow me on that? And that's a very powerful thing to know. All right? Is there any reason you guys are so weary today?
I think we were always here.
What?
It's been a long week.
Yeah, I'm with you on a long week. I'm pretty weary too. I haven't slept.
Statistically, people feel more tired on rainy days.
Might be true. Anyway, it's Friday, so thank God.
Yeah.
Let's get going with this idea. Thank God it's Friday and work through this one. That's for continuous time. Now I'm going to, what's the big benefit of Laplace? I mean, tell me, we did a lot with Fourier, we did a lot with Laplace. What's the one thing Laplace allowed us to do that Fourier didn't?
It converges easier, doesn't
Well,
it?
that is true. You can get more functions. Laplace transforms and more functions, but there's something else. We can do design with Laplace. Remember, we can do stability. We can talk about what? Anything stable if all the poles are in the left-hand plane. Remember that? Anything in the right-hand plane is unstable. And then when we build these little things, you remember how I showed you negative feedback? You could calculate the values of the forward and reverse feedback to get stability in a system that is inherently unstable. That's what I'm saying. Now, you'll get a lot more of that with Dr. Hung in your controls class, but that's important. This allows a lot of design. You can do a lot of synthesis, stability work, all sorts of design work with this. Remember when we realized functions using what? Capacitors and resistors and op-amps? Remember, we could take a function, any function, and we could easily create a circuit that would realize that function. It was for continuous time, I know it, but it was still something doable. Correct, class? That was the original computer stuff, and he remembers that one. For the original circuits, we literally just took amplifiers and took capacitors, resistors, and just started take wires out of a board and you'd start connecting them to all these things, and you could realize any of those transfer functions. We did this long ago. Now you guys, you do it on a computer and you do it with digital hardware now. You don't do it that way. Everything's digital signal processing. Now, what do you think the logical thing is if I want to look at a sampled signal? What do you think I'm going to do? And still have all the benefits of the Laplace transform. First I'm going to do is replace x of t by what? X of t sampled, right? Now, you don't write this down. Just listen. Let me go off on this one, but I want your attention. I'll tell you what to write. So the book doesn't do it this way. First I'm going to do is say x of t now is going to be sampled. I'm going to do it this way. I'm just going to say it's really x of t times an infinite series of delta functions of t minus nts. Here I'm going to let n equal 0 to infinity. This simply samples that in the interval of ts, just like we did before to get the TFT. You remember that? Now I go ahead and I put this in this integration. Don't write this down yet. When I put it in the integration, I have my x of what was s equal to the integral from 0 to infinity of this goofy thing. And it's multiplied by e to the minus st dt. Couple ways to go with this. I want you to look at this and note this. Don't write it down, just listen. You're writing it, that's okay. If you want to write, go ahead, but it's easier for me to explain it if you take a look at this and just follow me. Now, remember what I did last time I did this approach? I made the case that the only values of t that matter were at NTS, didn't I? Because that's when the delta function turns on. Do you agree with me? So that means this value right here is going to be x of NTS. You give me that one? Now what happens when I integrate this infinite series of delta functions times e to the minus st dt from 0 to infinity?
Sift out.
They're simply going to sift out the properties of e to the minus st replaced by NTS. Do you agree with me? And it's still going to have that what? Infinite series flavor to it, right? So you're still going to have this. And now you're going to have x of NTS, right? And then it's going to be e to the minus s times NTS. Now the only thing I've done there is went ahead and evaluated the delta functions. I evaluate the integration where the delta function turns on, correct? Y'all see that's starting to look real similar to a DTFT, isn't it? My next thing that I'm going to do is suppress TS, because anytime you have x of n, they never tell you what the sampling interval is. It's implied, so I'm going to get rid of that. Now I look at this, and this I'm going to just mention over here for a second. You don't need to write this down. Just listen to me and it'll make sense, and then I'll tell you what to write. Now, when I look at e to the minus s times NTS, I know that s is actually equal to sigma plus j omega, correct? I'm going to go ahead and I'm going to say this is equal to e to the minus, and it's going to be sigma plus j omega times NTS. Follow me so far? Keep watching. Now I'm going to say this is actually equal to e to the quantity sigma times Ts times the quantity e to the j omega Ts to the minus n power. I want you to just take a look at what I've done. I simply broke up that e to the business, all that stuff, into two parts, right? You all agree with this? Please watch this. Are you with me? You can write that down. You're going to see where we're going and why I'm going there. I'm using a Laplace transform, but now with a sampled sigma. Agree? All right, watch. What is this really? If I have e to the sigma ts, suppose sigma is 0.5 and ts is 0.05. Isn't that a value, e to the point, whatever, say 0.0025, right? That's a singular value, right? So I can really say that this can be replaced by something where this will look like a constant. It will look like rho. The book uses rho. It's just a constant. Forget about its value. It's some constant. Now what about the next thing? This e to the j omega ts. Do you remember what omega ts ended up being when we did the DTFT business, where we went from a continuous time Fourier transform to a discrete time? Most of you probably don't. But it actually is just going to be equal to capital omega. This part right here becomes just e to the j omega. So this part becomes that. Omega ts is capital omega.
Is that a row?
Yeah, the book uses rho.
Okay.
It's a symbol, it's not p, it's rho, and I'm using what the book's using. And what is this? It's to the minus n power, isn't it? Now, here's the deal. The book says, and all books say this is called a z transform. They said this is equal to z to the minus n, where z itself is equal to some constant rho e to the j omega. And now I'm going to write the actual DTFT right here. Z transform right here. Since this is z right here, The S that I've got here will be replaced with a Z, and now I can say that x of z, now it's a function of this z business, the rho and the e to the j omega, where the small omega times ts becomes capital omega. I can say x of z now is equal to the summation from n equals 0 to infinity of x of n times z to the minus n. Now we don't have an e to the minus n omega, or minus j n omega anymore. We just have z to the minus n. But z has omega built in. And it also has a condition that will allow a lot more to converge, because this value of rho all of a sudden makes this. This is the true z transform. It allows us to get convergence for a much wider range of functions. Follow me on this? One thing you should note about this too. I know this is new to you, but I'm trying to show you the continuity with all these transform pairs, why we're doing what we're doing. This is just like the Laplace transform for continuous time. It has all the benefits of design, all right, and stability analysis and things like this, and a wider range of values. But if you take a look at this, if you have any function that turns on at 0 only, that's where it starts, then you can get the DTFT of it if you have the z transform by just letting z be equal to e to the j omega. Do you see it? If z is just equal to e to the j omega, isn't this the DTFT for values, signals that are only, we've got non-zero values for n equals 0 or greater than 0? Are you with me? Now that's the real benefit of all this. Understand this? Now, I like to expose you to going through just a bunch of standard z transforms. You know, with me, you get about 4 or 5 transform pairs, right? And then from that, the rest of the stuff you need, you get with properties. You all know that. That's the general rule I have. You don't memorize 50 different transform pairs. You only need a handful, and the properties will get you where you're going. Same deal here, and I'm going to tell you about the z transform too. It is by far the most useful thing for doing any kind of stability work, and in radar we use it, we do all sorts of stuff. We use the DTFT too, because we just take the z transform and let z be equal to e to the j omega, and we do this. But with most things, the z transform is the gold standard for doing a lot of stability work, analysis, and design, and you can create a DTFT out of it. So now, without further ado, do some z transforms. I don't know where the other class is, but what I'm going to do is spend a lot of time showing you the power of all these transforms transforms in applications.
The other class just had their Laplace test.
What's that?
The other class just had their Laplace test.
Well, have they done DTFT yet?
No.
No.
So they're going to have fun when it gets to the filters, because they've got filters and stuff coming up, and I'd rather spend more time on applications. That's where it gets a little hairy. All right. Now, let's go ahead, and I'm going to write what the z transform is. X of z, what page is this on your book? This is a z transform. Summation n equals 0 to infinity of x of n times z to the minus n. And put down out here, z is actually equal to some value rho e to the j omega. So that capital omega is the capital omega in the DTFT. Anybody? What page number?
370.
All right, let's do so. By the way, you're going to get these in a heartbeat because you've done these things so many times. If we start with, usually I start with the delta function, delta of n. What's the pair of that? Just put it in there. If this is delta of n, remember it's not infinite for a sample thing, right? It's 1. What do you get for x of z? If I put delta n in here, right? Where does it turn on it? N equals 0, right? N equals 0. N equals 0. What is z to the 0?
1.
1. I think everybody saw that coming. Right? What's the next likely one? I like to do, this is actually a property, but I like to throw this in here. Delta of n minus, say, q. I think the book uses Fibonacci. What's that going to be? This is actually a property. It's a shift property, but just take a look.
Negative q, or negative qz.
All right. It's z, right, to the minus q times what? That's it, isn't it? Look, you're used to, oh, there's no s in front of it. You don't need it. Z is the thing that it has the s ingrained in. You follow me? It's z to the minus q.
Yeah.
Y'all see that in the book? What page of the properties on both?
Figure 268, 2 pages prior.
All right. So 368 is the page with these pairs. Now, after that, the one I like to do is this one. I like to do a to the n u of n. Now, we could do that, can't we? We can do that one. I think you know what the answer is. I want to do this one just to make sure everybody's head's on straight and it's warm in here. So, follow me on that. If I have a to the n u of n as my x of n, then this thing becomes what? The summation of a to the n, since it starts at n equals 0, we just let our count start where it's supposed to, at 0, then it's times z to the minus n goes from 0 to infinity. That's really what? The summation of a, right, over z to the n equals 0 to infinity. Do you remember what that goes to? You're going to take a over n to the lower power, right, n equals 0 or 1, minus a over z over here as n goes to infinity. But that would be 0. And I'm going to put it down, I'll show you why. Minus a over z to the actual infinity power. And that's over 1 minus what? Just a over z. Just write that down, I'm going to show you something. Now we look at something that talks about when the z transform exists. It's called the region of convergence. So write this down. This is going to be the region of convergence. Or ROC. When you look at this, just look at this summation for a second. Don't look over here. If I have 1 to the n, some from 0 to infinity, is that a finite value? If I have 1 plus 1 plus 1 plus 1 plus 1, blah, out to infinity, is that finite? No. What if I have 1/2 to the n? Sum from 0 to infinity. Yes, right? And the condition for this to work is that the magnitude of a over z has to be less than 1. This would be the regions of convergence. Or you could say that a times z to the minus 1 is less than 1, right? Or it would be that what? Z, right there, if this is greater than, if a over z, right there, is less than 1, then z has to be greater than a. Do y'all agree with that, class? For the region of convergence. For this to be less than 1. Do you agree with that? And this is called the region of convergence. I'll show you what this looks like. Maybe I can give you a glimpse right here. When you actually see this, you're going to see something where you'll have, I can't go this route right now, but it's going to look at something where the radial distance rho, where I have rho e to the j omega, the radial distance rho is the thing that defines the region of convergence. And we'll get there in a second. Let me keep going on this. So really, if this is the case, then this term goes away.
That term, was that to the infinity? Okay, so-
That will go away because of the region of convergence. And then the way this is usually written, I shouldn't say always, but the way this is usually written will be simply 1 over 1 minus a times z to the minus 1. Sometimes you see z over z minus a. They're both the same. All right? They don't, one's the same as the other because you're just multiplying by top and bottom by z on the second one. So that's this one. Now, after that, what happens to u to the n? And out here, I should put down, this is the region of convergence is for z to be greater than a. Well, what is u to the n? Take a look at this, you can get it just by inspection. Doesn't this look like 1 to the n times u of n?
Mhm.
So it is that same thing, right? Only with a going to 1, and therefore it's going to be 1 over 1 minus z to the minus 1, or z over z minus 1, and then the region of convergence for this one specifically is going to be 1. Z is greater than 1 for this one. It won't mean a lot to you until you see why the region of convergence is used. But right now, this is necessary for the transform to exist. Are you okay with that? Now, let's see, next one I'm going to do. Have I dealt with that? Just seeing if I'm going to have. All right, I got the basic properties. I mean, the basic pairing. Now, I want to just go through this. Really, these are the pairings right here. The rest of the stuff we'll get from properties. Are you okay, class? So, let me go through some of the properties. Linearity is the first property. I almost don't even want to do this, but I will. If you have x of n goes to capital X of z, then if you put a small a here, you put a small a here. If you had a second function, b times y of n here, it would just be added on plus b times capital Y of z here. That's linearity in a nutshell. That's one that you know. Anytime you have this is called the right shift property, but I'm going to write it down for you. If you have x of n minus q times u of n minus q, over here, that will just be e to the minus q times the actual value of x of z. Now, I suppose I could prove that one. Some of these, I think you can see them, but I'm going to prove at least a few of these. All right, it assumes for this one that we know x of n goes to x of z. Now, how come it works this way? Let me go from the basic definition here, and I'm going to work right here. You don't need to write this down, but now I'm going to get this transform of that. Suppose I have the summation here of n still goes from 0 to infinity, but now I have x of n minus q here times u of n minus q here times z to the minus n. Work with me on this one just for a second. You don't have to write it down, just look. What really happens when I have the u of n minus q? It starts where? At n equals q, right? And now I can get rid of this. Now I look at this right here, and I say what I'm going to do is a change of variable. Remember, I'm trying to evaluate this. So when I do it, I'm going to let, for this one, I'm just going to let n minus q be equal to something, I'll call it m. All right? And that means n is equal to m plus q. So when I have this transform right here, it's equal to the summation now of x of m and z to the minus n, or z to the minus m times z to the minus q. I put n here and replaced n by n plus q. My count started at n equals q before, right? But now q here would be at what? Q would be equal to what? N minus m, correct, class? So if this started at what? n minus q right here, pardon me?
Oh, thank you.
I'm sorry, m, I should actually say m here.
Negative.
Yeah, I just, what you call it, since I'm replacing this with m, I'm replacing, it's gonna start at n minus q as m, and that would be 0 then, right here. And it would go to 0 to infinity, because anytime you add or subtract anything, find it. Now, what is that actually? Can you see how you can take the z to the minus q in front? Because the summation is on, this will be on m now. And if I take z to the minus q in front here, I can say that this is the z transform times z to the minus q. That's what that does. This is just like the DTFT with a shifting operation where you get a time delay. The thing about this is so important to understand is you have to shift x of n minus q times a u of n minus q. In other words, both of these things have to shift the same amount. Follow me? If you just have x of n minus q, then it won't work. And I can show you why in a second. Follow me, class? Just think about that for a second. Let me do the other one. Now, suppose I want the property x of n minus q. Just this. Now there's not that u of n minus q. Follow me? Please watch this. You got me on this, class? So now it doesn't shift and start at a certain place. Now it hasn't shifted. The origin still is going to be at n equals 0 for the z transform. Now the z transform of this will be equal to the summation from n equals 0 to infinity of x of n minus q times z to the minus n. With me, class? Let's do it this way. Let's not make it general minus q, make it minus 1. We'll go one at a time. All right? We're just shifting by 1. Now keep watching. When I look at this right here, I need a variable transform because I need to get a z to the some power by itself to make it look like a z transform sum. So when I do this, I'm going to take n minus 1 and call it equal to m. So now I've got this summation, and now I have x of m, and then it's going to be z to the minus n, but n is equal to minus m times z to the minus 1. You'll notice when I replace n here by m plus 1, I get z to the minus m times z to the minus 1, right here, right? And then since it sums in m will start at not 0 but minus 1. So m will start at minus 1 to infinity. Y'all see this, guys? Because what? N started at 0, therefore m starts at minus 1. I'm changing the index. Does everybody see that, people? Now keep watching, let me just finish this. Now what happens here? The very first point, when m is equal to minus 1, I get x of minus 1, right? But then I get, what happens here? I got minus of minus 1, or 1 times z to the minus 1 is z to the 0, or times z to the 0. Then I get plus the summation, keep watching this. Now m will be equal to 0 to infinity, right? Of x of m here times z to the what? It'd be z to the minus 1 comes out in front, z to the minus m is there. Do you all see that? Right here, when m is 0, I get z to the minus 1 here, right? What I'm really saying is when it's minus 1, I'm going to break that term out by itself. At minus 1, when m is minus 1, I get x to the minus 1 times z to the what? Minus 1 is plus 1 times z to the minus 1 is z to the 0 is 1. Correct, class? So I get this first part. Then, when m is equal, from that point on, I can just take the z to the minus 1 out in front, right? And then have this. And what is this? The definition of the z transform. So I can really say for this one, it's equal to x of minus 1 and then it's gonna be plus z to the minus 1 times x of z. So that's what happens when you get a simple shift of 1. If you get a shift of 2, I have to add something to it. I'm already out of time. But this is the introduction to the z transform, and I'll give you the properties on Monday. They're very straightforward. The properties, I'm going to ask you to make sure you do the homework I give you. The thing about z transforms is there's a lot of parallels to the DTFT, but there are some subtle differences with all these delays. Or if I add, instead of n minus q, it could be n plus q. There's some things that aren't apparent until I go through the examples with you. So stay sharp and do the homework.